Welcome to today's paper reading. Today's paper is titled OWL, a Large Language Model for IT Operations. This paper was published at ICLR 2024 by Hongcheng and colleagues from Beihang University and Cloudwise Research. The OWL model is a specialized large language model designed for IT operations. It is trained on AllInstruct, a dataset rich in IT-related information. To address the limitation of maximum input length, the authors proposed the homogeneous Markov context extension method, which enhances the model's ability to understand context and improves performance. Additionally, the mixture of adapter strategy is employed to efficiently tune parameters across different domains or tasks, further enhancing the model's performance on various IT tasks. Large language models, such as GPT-3, have shown significant advancements with 175 billion parameters, outperforming previous models in various tasks. These models exhibit capabilities like few-shot prompting, which are not seen in smaller models. While general LLMs cover a wide range of subjects, domain-specific models, particularly in science and medicine, have shown exceptional performance. This highlights the need for specialized models in IT operations, which face unique challenges due to their complex terminology. The OWL model, introduced in this paper, is trained on a dataset called AllInstruct, which includes 9 domains within operations and maintenance. The model uses data augmentation and is evaluated using OWLbench, a bilingual benchmark for IT-related tasks. The construction of the AllInstruct dataset involves several key steps. Initially, 25 subject matter experts in operations and maintenance, O&M, were engaged to create 2,000 single-turn and 1,000 multi-turn seed data instances. This seed data forms the foundation for the dataset. Following this, the dataset was augmented to include 9,118 single-turn dialogues, with quality ensured through GPT-4 and manual validation. A dual validation process, combining GPT-4 scoring and manual inspection, was employed to maintain high data quality standards, ensuring the integrity and reliability of the dataset. Figure 1 illustrates the 4 key phases involved in the construction of AllInstruct and the subsequent training process of our OWL model. These phases include the initial seed data collection, the generation of diverse instructions, the augmentation of data to enhance quality and diversity, and finally, the evaluation and fine-tuning of the model. The training process integrates data from various operations and maintenance, O&M, domains, ensuring a comprehensive and robust model capable of handling a wide range of IT-related tasks. This structured approach is crucial for the development of a specialized large language model tailored to the complexities of IT operations. Table 1 provides a statistical analysis of the single-turn and multi-turn scenarios within the AllInstruct dataset. The table highlights that there are 2,000 single-turn and 1,000 multi-turn seed data instances. It also shows that the total number of dialogues is 9,118 for single-turn and 8,740 for multi-turn scenarios. Additionally, the average number of turns per dialogue is 1 for single-turn and 2.9 for multi-turn, indicating a higher complexity in multi-turn dialogues. These statistics are crucial for understanding the structure and complexity of the dialogues in the dataset, which is essential for training and evaluating models in the operations and maintenance domain. Figure 2 presents a visual representation of the keyword cloud within the AllInstruct dataset. This keyword cloud is constructed based on the frequency of word occurrences. Notably, words such as data and service appear more frequently, indicating their prominence in the dataset. This visualization helps in understanding the key thematic areas and the relative importance of different terms in the context of operations and maintenance. OWLbench has been developed to evaluate the performance of large language models specifically in the context of operations and maintenance. This benchmark is crucial as it fills a significant gap in our ability to assess and compare models within this area. The benchmark is divided into 2 main parts: a Q&A section with 317 entries and a multiple-choice section containing 1,000 questions. It is designed to be bilingual and covers a wide range of subdomains, ensuring a comprehensive and diverse evaluation. The data used in OWLbench is collected from real-world scenario-based examination questions, without any modification or expansion through GPT-4, ensuring the authenticity and relevance of the questions. Table 2 provides a detailed statistical analysis of the OWLbench, a bilingual benchmark designed for evaluating large language models in the context of operations and maintenance, O&M. The table highlights the distribution of questions across 9 distinct subdomains, including information security, application, system architecture, software architecture, middleware, network, operating system, infrastructure, and database. It also specifies the number of Q&A entries at 317 and the number of multiple-choice questions at 1,000. This statistical breakdown is crucial for understanding the breadth and depth of the OWLbench, which aims to comprehensively assess model performance in real-world industrial scenarios. To improve compatibility with both natural language and IT-related data, the authors expanded the word vocabulary size from 32,000 to 48,553. This expansion enhances the model's ability to handle IT operation data. Inspired by the naive Bayes-based context extension, NBC, the authors proposed the homogeneous Markov context extension method, HMC, which better accommodates the continuous nature of input data. Additionally, for efficient parameter tuning, the authors employed a mixture of adapters strategy, using lightweight LoRa adapters to facilitate cross-domain and cross-task transfer. The evaluation of OWL's performance is conducted on OWLbench and various downstream tasks. OWLbench tests the hypothesis that training on high-quality data improves results in the operation and maintenance area. Downstream tasks, such as log parsing and anomaly detection, investigate OWL's generalization capability. The experimental setup uses Llama 2-13b as the base model, with specific parameters for instruction tuning and LoRa training. Table 3 presents the average scores of various large language models on the Q&A part of OWLbench, with scores ranging from 1 to 10. The models evaluated include Llama 2-13b, ChatGLM 6b, ChatGLM 2-6b, Qwen 7b, InternLM 7b, and OWL 13b. Notably, OWL 13b achieved the highest score of 8.86, indicating superior performance in answering questions related to operation and maintenance problems. The scores reflect the model's capabilities in comprehensive processing and logical reasoning, with a small variance observed among the models, suggesting a high level of performance across the board. Figure 3 presents the pairwise scores of various models on the Q&A test within the OWLbench framework. Notably, the OWL model achieves the highest score, indicating its superior performance. However, the figure also highlights a significant number of draws between models, suggesting that in many instances, both models generate satisfactory answers according to GPT-4. Overall, the models exhibit strong performance with only a small variance in their scores, reflecting consistency in their Q&A capabilities. Figure 4 presents the 0-shot and 5-shot results of multiple-choice questions on OWLbench. It highlights that ChatGPT has the highest average scores across various domains, with OWL closely following and outperforming other models. Notably, OWL achieves higher scores than ChatGPT in the system architecture domain, indicating its strong performance in specific areas. Table 4 presents the results of OWL on long context inference using various techniques. The table shows that OWL 13b's perplexity, PPL, increases proportionally with the sequence length. In contrast, OWL 13b combined with NBC, SU, 2023, maintains a lower PPL across different sequence lengths. Notably, OWL 13b combined with HMC demonstrates the best stability in PPL, indicating its effectiveness in handling long context inputs without fine-tuning. These results highlight the superiority of HMC in enhancing the context processing capabilities of large language models. Table 5 presents the results of ablation experiments comparing the performance of multiple-choice tasks with and without the mixture of adapter, MOA, strategy. The data shows that the MOA strategy significantly improves zero-shot testing accuracies across various categories such as middleware, information security, and infrastructure. Notably, the OWL model with MOA outperforms the OWL model without MOA and even the OWL model fine-tuned with LoRa. This demonstrates the effectiveness of the MOA strategy in enhancing the model's performance in zero-shot scenarios. Table 6 presents the results of log anomaly detection in the zero-shot scenario. Notably, OWL demonstrates superior performance compared to existing methods, even those trained on thousands of logs. Specifically, OWL shows an average F1 score improvement of 6.5% across two datasets when compared to ChatGPT, log prompt. However, the overall performance in the zero-shot scenario remains modest, highlighting the challenges in leveraging large language models for anomaly detection without prior training data. In this paper, the authors introduced the OWL, a large language model specifically designed for IT operations. To enhance the model's generalization capabilities, they collect the OWL-instruct dataset, which includes a variety of IT-related tasks. Additionally, they present the OWL bench evaluation benchmark dataset, covering 9 operation and maintenance domains. The authors also propose the HMCE method to extend the context and the mixture of adapter strategy to improve performance. Extensive experiments on OWL bench show the effectiveness of the OWL model. This research was partially supported by the National Natural Science Foundation of China, with grant numbers 622766017, U1636211, and 616720081. Additionally, the State Key Laboratory of Software Development Environment provided support through grant number SKLSD 2021-ZX18. Acknowledgement of these funding sources is essential to recognize the importance of financial support in enabling this research. Thank you for watching.